Great. So, welcome again. Good morning. It's for me a great pleasure to introduce Enrico Baldinocci, who is lecturing from Western Australia. And his topic, is about the levy flight foraging hypothesis. So let's see what it is. Thank you, Enrico.
Thanks a lot for having me. It's a great pleasure for me to be part of this workshop. Unfortunately, I cannot move from Western Australia till the pandemic goes, so it will take a while for me to meet all you guys in person. But so the levy foraging hypothesis is something related with optimal search strategy. So it's a topic of practical importance because you can think about the algorithm for web search engines, or unfortunately military targets. So some of the articles related to this topic are called how to chase a submarine, for instance. But for me, I mean, the interest comes from nature and environment. And so it's a theory that became popular year after year. It started in the late 80s with the assumption that sometimes a power law distribution of flight distance could be better optimize the search efficiency because of the reduction of oversampling. So for instance, in this picture on the left, we have a levy flight, and on the right, we have a standard Gaussian random walk. And you may think that if you follow a random walk to search for food, may be kind of inconvenient because you keep revisiting the same areas. So if there is no food there, the forager waits a long time before separating from the original position and explore other regions. So in a sense, a levy distribution can be more effective to explore for the space exploration. And a number of problems arose in the biological community, thinking whether or not such type of patterns could be produced by a memory effect of the forager knowing the environment better and better after searches, after different searches, or maybe due to the fractal distribution of targets. So suppose that the preys are distributed like a fractal, with the fractal dimension, then maybe the fractional nature of the levy flight is somehow resembling the patterns of the preys. But again, in the 90s or so, a group of people led by the Brazilian physicist Gandhi Viswanathan tried to address the problem in a sort of purely mathematical attitude, well, and also checking with the experiments we will see, but somehow trying to address the problem of animal foraging in terms of optimal strategies. What are the strategies that optimize the outcome for the forager? And so as I was saying, this team with Gandhi Viswanathan was playing somehow on two fields. One was the real field of the biological experiments. So they were taking these big birds called wandering albatrosses. They are really big birds, are probably the birds with larger wingspan. So they take some effort they need some effort to take off. So once they fly, they better fly for a long distance. And they were putting sensors attached to the legs of the birds in order to detect when the birds were diving in order to fish, in order to search food. So if the sensor was dry, the bird was not diving. And so they were assuming that the bird was flying, for instance, say at constant speed. And in this way, they were measuring the distance, hopefully between one nose diving and the next one. So this is the animal. This is the wandering albatross. If you see, it's a kind of a huge, it's big animal. And so the other side in which the team was playing is the one of the mathematical framework to set this problem in. So there is this famous paper in which they show that if the target is sparse and the target sites can be visited anytime, so that the prey is reproduced fast, then the best strategy for the hunter is the one of power law distribution corresponding to the inverse square law. Okay, and after that there was a huge debate which is still going on today, because of course there are people who believe that the inverse law strategy is always the best one. Others that say, well, it's more complicated than that, because of course the world is complex. So there could be, for instance, there are several structural objections to this theory, because first of all, assuming that the animal wants to optimize a specific parameter is a little bit simplistic from the scientific point of view, because the animal doesn't only need to eat, it has a number of needs. So optimizing only one is a little bit too simplistic, maybe. Also, all these classical models don't take into account the experience developed by the animal, so the memory effect. Also, the game is typically, when I say the optimal strategy, I should specify the optimal strategy between Levy or Brownian motions. If one tries also to comprise other possible strategies, the situation becomes more complicated. And also, if one really wants to do a biologically precise model, one should take into account the density of prey, the environmental condition, and so on. And one last objection, which seems naive, but it's actually much deeper than what it sounds at the first time. It's very difficult to deal with animals and to distinguish what they are doing. So are they really looking for food, or are they searching anything? So when we see an animal moving, it's not clear that the animal is really engaged in a particular search or not, okay? Maybe it's just traveling between locations, or maybe it's doing something else. And actually, in the case of wandering albatrosses, well, actually the team, after discovered that the data that they first collected were not so precise, because the albatrosses were not only looking for food, were also nesting in an island in the middle of the ocean or the sea. So the sensor was remaining dry, not because the albatross was flying, but because they were nesting on the island. So it's kind of difficult to distinguish what kind of action an animal is doing. And there are a number of papers which bitterly criticize this Levy flight foraging hypothesis. But the fact is that whether you like the hypothesis or not, the numbers of papers dealing with that, either to confirm it or to refuse it, increases year after year. And I think it's a very beautiful and very interesting topic. So with Serena Di Piero and Giovanni Giacomini, we decided to look a bit into this matter a little closer. So I will present the initial results that we have obtained with the warning that everything is kept at the simplest possible level. So our strategy was to try to study not the most biological complete situation, but the simplest possible scenario in order to detect the structural difficulties, the problems that arise, and the surprising phenomena that can be created by very simple biological patterns. So differently from the existing literature, we focused on making somehow a number of precise assumptions on the efficiency functional that we are going to optimize. So in a sense, our philosophy is that there is not a precise given functional in nature that we want to model, but somehow a variety of functionals that represent under different perspectives the maximal amount of food that the forager obtains in a given amount of time over the energy, in some sense, spent to accomplish this goal, okay? And we will look, as I was saying, at very simple scenarios. So for instance, the case in which you have just one single target close to the forager, and this you may think it's obvious, right? The food is there, the forager should eat it, but this is already revealing a number of special features of the problem taking into account. Then we consider the case in which the targets are sparsely distributed, the case in which one has a single target located far away, and the case in which there are two targets, one close and one far. And for simplicity, we ran the model only in 1D. I mean, you can do more, you can address the high dimensional case, but for simplicity, and also because the literature has some controversies about higher dimensional models, we keep the situation as simple as possible, considering the 1D case. And differently from the existing literature, we took into account the case in which the forager follows a fractional heat equation. So in most of the literature, the model was a little bit discrete. So the forager was restarting the movement after each time it hits a target. But we think it's simpler to think that the forager diffuses and eats the targets while diffusing. Also, in many of the previous literature, several additional parameters were taken into account related to the direct vision, with the idea that if the forager is close enough to the target, then a direct vision kicks in for the forager to reach the target. And this, I mean, it's not so clear from the mathematical point of view, because it truncates the power law. So somehow every computation that arises from this additional parameter requires some discussion on the influence of this additional parameter on the optimization problem, okay? And this can be significant, especially if you think that the power law is diverging near the origin. Also, in most of the literature, the authors were considering the time of food that the forager eats at a certain time, we do time averages, which also I think it's kind of consistent with the idea. It doesn't really matter if you eat now, it matters if you eat in average. And one technical, but I think interesting thing, we took into account the role played by normalizing constants. This is a technical point, but I try to discuss it more precisely in the course of the technical part of the talk. And so, as I was saying, we put an effort in keeping the structure as simple as possible. And the advantage of doing so is that you find solutions in closed form. Closed form, I means relying only on elementary functions like sine, cosine, or in the worst case, the gamma function or the zeta function. So you don't need any special numerics to plot your solutions because your solutions are very well-known functions. And so the main model is as simple as possible. So we took a fractional heat equation, so a linear problem starting with a source located at the origin. So for us, the forager starts at the origin and then diffuses according to a fractional heat equation. We take the fractional parameter S to be larger than 1/2. We will see in a second why this restriction. We have a diffusion parameter that we call kappa to the power 2s. Well, you can call it kappa if you like, but I think kappa to the power 2s is nicer because it was matching with the order of the diffusive operator, okay? And we already distinguish two possible cases in this equation. The case in which kappa is equal to 1, which is the one that is studied in the literature. Kappa equal to 1, I mean, looks like the obvious normalization. But we also were a little bit picky and we said maybe it's also interesting to study the case in which kappa is equal to this strange number, kappa s, which looks like a weird constant, but it's the constant which comes from the probabilistic interpretation of the Levy random walk. So if you think that the animal doesn't really know fractional diffusion, but that the fractional diffusion is the limit outcome of a sort of random movement of the animal, well, it may be physically and biologically consistent to take into account this constant that depends on S. Okay. Of course, if you are just interested in one single equation, this is just a constant. But since we want to optimize in the parameter S, well, the constant can play a role in the optimization problem. So it's worth to be pedantic and also consider this possible situation. Then we have to introduce the notion of foraging success. And we said, well, the easiest thing to do is that there is a foraging success when the predator meets the prey. And so the success is proportional to both the density of predators at a given point and the numbers of preys at the given point. The more the predators and the more the preys, the more the success of the interaction. And remember that we are considering a prey which is replaced immediately after being eaten. And this is the case, for instance, if you think about web searches, or it's more or less natural if you think about bees in a flower, because the flower will replace the nectar quite fast, or if you think about plankton in the sea, because the plankton will be moved around by the waves. So it's not such an unrealistic assumption. In any case, this is one of the typical assumptions made in the framework of Levy flights. Then, this is not the only thing that we have to take into account if we want to model a foraging strategy, because of course, going around and eating prey has a cost for the predator. So we divide this foraging success functional by another term that we call C, which accounts for the consumption of energy due to the journey, okay? And the ratio between this quantity and this term C is what we call the efficiency functional. Better to say what we call an efficiency functional. Because remember that we already have two choices for the foraging success functional. One choice is coming from kappa equal to 1, one choice is kappa equal to kappa s. And also the consumption of energy can due to many things. So, for instance, one can just divide by the total time t, or one can consider the average mean displacement. The average mean displacement is the length traveled by the forager in the given time, and so this can be also computed explicitly from the equation. And so you have several possibilities for this efficiency functional. And of course,
sorry,
yep.
Sorry, Enrico. In the previous formula, the output doesn't depend on capital T here. Oh, yeah, it's there. Power of T. Okay, thank you. Yeah. Okay.
Yes, this is tricky, right? Because when you pass from the random walk to the diffusion, the dependence on time is not linear, right? Because the heat equation doesn't scale linearly, and so this is why you have very different behaviors if you divide by the total time traveled or you divide by the average length. I mean, in these models, you have two different objects.
And this is for the fundamental solution, right?
Yes, exactly. So for the moment, everything is as simple as possible.
Okay.
One forager diffusing.
Okay.
And let's see if this is a trivial case or if it's already produces some non-trivial pattern. Because this would be for me the challenge, right? Because it's a very complex problem. And my first question was to understand whether or not the complexity was due to the biological complication of a very sophisticated world in which we have to take into account many parameters, or if even the simplest possible scenario was producing something which creates a sort of debatable answer. So the answers that were around in the literature, I mean, people fight, say, oh, of course, the animals diffuse like this, and the optimal strategy is this, but the others say it's not true. This experiment shows exactly the converse, okay? Or even sometimes your experiment shows exactly the converse. And we will see that I think this is the typical situation in which everybody's right. And you will see why in a second, even in the simplest possible scenario. Okay, so one philosophical question is which is the right efficiency functional to take into account. So for that, I'm not a philosopher, so I don't think there is a right functional. It really depends on taste. After all, for a person or for an animal, one thing as a priority, and for another thing as a priority. And if you think that this is a crazy idea, well, when they checked what happened to the albatrosses and they rechecked the data, well, they found that for some individuals, the Levy flight seemed to be the optimal strategy that they were implemented. For other individuals, there was instead the Gaussian strategy that seemed optimal to them. So after all, it may well be that different animals have different priorities and measure the success depending on slightly different efficiency functions. Okay, so we have already 4 of them, and we can see what happens if you just do these small changes in the functions. So as I was saying, the first case that we study, I mean, just for this is just a sanity check, right? We want to understand what happens if you put the prey at the origin. So the prey is there, the forager shouldn't do anything, just eat the prey. That's not like this. I mean, this is something that you may experience also in nature. I mean, it's not obvious that the forager notices that there is a prey so close to it. So since the forager has the idea that they have to diffuse to look for the prey, they may be not so attentive and not find the prey, even if it's located so close to them. And so let's see what happens if you run the mathematics. The foraging success functional is explicit. Everything can be computed, and it's this function here. This kappa has already 2 possible choices, kappa equal to 1 and kappa equal to kappa s. And then I have other 2 cases depending on whether I divide by the total time or by the total length. Okay, so if I take kappa equal to 1 and I divide by the total time, the optimal is s equal to 1/2. So this is a good news if you believe in the Levy foraging hypothesis, because it tells you that this is in line with the computations showing optimality for the inverse square law. But it's counterintuitive if you believe that the prey is there, the animal should just eat it. But this is already instructive because it tells us that the reason for which the optimal is s equal to 1/2 is that our concept that the lower the exponent, the faster the diffusion, is inaccurate, because the lower the s, it's true that the jumps increase, but also the regularity of the solution decreases. So when s is small, you have some distribution of predators going far away, and they will miss the prey, no matter how far they go. But since the heat equation is not very much regularizing, you still have a high peak at the origin, and that high peak will still be able to eat the prey. Okay, so the optimal is still s equal 1/2. This was surprising for me. I overlooked this at the beginning, the effect of the loss of regularity of the heat equation, because I was thinking that the smaller the s, the faster the diffusion, but that's not exactly like this. However, it's true that s equal to 1/2 is optimal, but it's extremely unstable. So the counterpart of the optimality is that there is a pessimizer at a value st, which converges to 1/2 when t becomes very large. So maybe the Levy pattern is better from the theoretical point of view, but the Poisson strategy, the one corresponding to a Gaussian random walk, happens to be more reliable. So let me show the picture of the energy, of the efficiency function in this case. So for small time, you have infinite efficiency for s equal 1/2 and the decreasing function. But then if time passes, you see that you produce a minimum here, and this minimum gets closer and closer to s equal 1/2. So this is already a case which shows why it's difficult to decide in nature what the optimal strategy is. Because for a very long time, it is completely true that the optimal strategy is still the one corresponding to the inverse square law, but it's almost unfeasible. It's too risky for an animal to choose this strategy, because if time passes by, unless the animal is very careful to choose the parameter equal to s equal to 1/2, precisely equal to s equal to 1/2, then the animal may risk to fall into the minimum rather than into the infinite maximum. So it may be safer, though less convenient, to opt for the classical Gaussian strategy, in which you have a local maximum here. Okay. And again, so I don't have much time probably, but for instance, even if you consider the case of a different kappa, you have a kind of bifurcation. You produce a local minimum close to the optimizer 1/2, and a local maximum close to 1. So this case, I'm just changing the constant, but this change produces a dramatic change in the optimizing functional, because now s equal to 1/2 is the maximum, and s equal to 1, corresponding to the classical case, is always the worst possibility. Nevertheless, again, for long times, the s equal 1/2 case becomes very, very unstable, and the functional develops a maximum which is very close to s equal 1/2. So again, the scenario is complicated like that. Yes, there are unstable situations like that also if you divide by the length. Again, this is a very dramatic bifurcation in the sense that for small t, the optimizer is s equal to 1/2, but for large t, the optimizer, oh, sorry, this is a typo. The optimizer is s equal to 1, not t equal to 1, of course. So this is really a bifurcation of the monotonicity of the optimal energy functional. So for small time, it's monotone decreasing. For large time, it's monotone increasing. And the situation changes again if you change the constant. But again, for large time, the optimal strategy becomes closer and closer to the classical one. Okay, so this in a sense says that for large time, the forager doesn't need to move much. The case of a sparse lattice can be reduced to this one, just because when the lattice is very sparse, basically you only see the origin in the limit. The other case of interest is the one of a remote single prey. Also, in this case, one can compute precisely the foraging success function, and as you see again, you have very explicit functions around, and you can consider again the 4 cases given, for instance, by the diffusion parameter equal to 1 and the penalization parameter given by time. This is a little bit tricky, right? Because in a sense, here you are forcing the prey to move. So in this case, for instance, the foraging success is 0 when s is equal to 1, suggesting that the Gaussian strategy is always the worst. Nevertheless, when L is small, so the prey is nearby, the optimizer is close to 1, so you don't need to jump much. But when you have a large distance, then the optimizer gets closer to S equal 1/2. This suggests that in this case, the levy movements are better for sparse environments. So you have a situation in which the maximizer is close to 1, and then when you move the prey far away, then the optimizer moves towards S equal to 1/2, and you end up having a monotone function. If you just change the diffusion coefficients, well, again, for small length, the optimizer is for S equal to 1. For intermediate length, you develop an interior maximum, and for large length, the optimizer is in S equal to 1/2. So again, you have a situation in which you change the monotonicity of your optimizing functional, but you have intermediate regimes with intermediate values of the optimizers. And let me say that intermediate values between 1 and 1/2 are actually observed in practice in many situations, and so they may well arise in patterns like this, for instance. Yes, and there are other cases that one can take into account. For instance, the case in which you divide not by the time, but by the length. And this is a tricky case because if you divide by the time itself doesn't play any role. It only plays the role the distance L from the prey. But in this case, both L and T play a role. So the special case is when L is a power of T. In this case, the function will become independent on the parameter. So this looks like the natural scaling for this problem. And in this case, you have precisely an intermediate optimizer between the case S equal 1/2 and S equal to 1. Well, you would argue that the intermediate is the average between 1/2 and 1, say 0.75. Well, almost in the case that the value that we find is very close to 0.8, as you see in both the cases. But this is somehow an indication that intermediate patterns can actually be consistent with the model. And the remote single prey, again, you can reduce it to the previous case just because when you have a remote single prey, it's like sending L to infinity, so you reduce to the previous case. So in a nutshell, so our strategy was to understand complex phenomena, to be humble and start with simple cases, expressing all the assumptions clearly with models that are explicitly written with boring technical mathematical formulas, but at least to avoid ambiguity. So better to be boring than being ambiguous for us. And whenever possible, rather than running simulations, to use explicit solutions with well-known functions so that we can really find explicitly the optimizers, keeping track of the structural constants, because sometimes one is tempted to say, oh, it's just a constant, I don't care. But after all, if the constant depends on the parameter in which you want to optimize, it's better to keep this constant because it can affect the functional. And we saw some structural differences, for instance, in keeping the dependence on S on the diffusion coefficient, and also be somehow democratic and let the different animals decide what is best for them, what is the efficiency functional that they want to optimize, detecting possible differences according to the choice of the functional. And also appreciate that the bifurcation phenomena occurs when you change the time or the space scale. And in general, many situations may end up to be unstable in the sense that the theoretical optimizer can be very hard to attain. And so again, a possible strategy could be the one of not looking for the optimal, but looking for the safest possibility. Okay, and with this, I think that my time is over. So I just want to thank the audience for their patience and attention, and the wildlife for their mathematical creativity. And I stop here.
Thank you, Enrico, for this beautiful talk. We are a little bit late, but maybe this is certainly a topic that deserves some short questions. So anyone in the audience wants to say something, comment something?
I have a comment, actually. So
Please.
The Levy flight paradigm has already also, this is not a surprise, maybe, penetrated optimization theory, where people use, instead of the, the vanilla stochastic gradient method, they use Levy flight stochastic gradient. And that can be very advantageous for global optimization. But this is a field of exploration, I think, that is interesting. This is just a comment.
Yeah. Thank you, Gunther. There is something that, for the, Enrico, for the Laplacian, for the fractional Laplacian S equal 1/2, I mean, when you look at it from the perspective of controllability, this is a critical exponent, right? So the reason being simply that, I mean, if you are just thinking on a bounded domain, I know you are on the whole line, but when you are in a bounded domain with irregular boundary conditions, for S equal 1/2, the eigenvalues of the fractional Laplacian grow like the index. So lambda j will be asymptotic to a constant times j, right? Mm-hmm. And then this is the critical exponent in which the sum of 1/λ diverges, right? And this is not good from the perspective of the controllability, because it means somehow that the spectrum is too tight. I mean, the eigencomponents are too close to each other from a time-dependent perspective. This is related to the classical theorem of Munch, right? That says that in order to get density of polynomials, it's sufficient to take powers, exponents, so that the sum of the inverses diverges. So in some sense, it's just the case in which you lose complete control of the system, right? But just sharply, right? So, it could also be that not having full control of the system is good in some sense when you want to explore, right? In the sense that not everything is completely predictable. But so my question is, Enrico, do you have any other indication of why S equal 1/2 is somehow critical? It's also critical, I think, from the elliptic regularity theory that you know better than anyone else, right? In the sense that you lose the H2S regularity, I think, right?
Yeah, so at this level, there is one thing that I really wanted to avoid, which is this. So I wanted to be able of speaking of the average mean displacement. So I want to say, okay, the animal traveled in average this distance. So what I do, I take the distance and I average it out. Now, this quantity is only finite when S is larger than 1/2. When S is equal to 1/2, this quantity becomes infinite. Now, let me say that some of the literature don't agree with this choice, because they introduce additional parameters to make this quantity finite. Others play another trick. They say, okay, this quantity is infinite, but what if I put an exponent here that makes this quantity finite? I wanted to avoid that, because my impression is that if you want to make this quantity finite for every S, you have to put an exponent here that depends on S. And so the constants will also depend on this exponent that depends on S. So while conceptually, if you just care about dimensionality, it's a very fair game, But if you care about constants that can appear in the energy functional, I would avoid such a controversy, at least at the first stage. That's also why I put S bigger than 1/2 to start with. On the other hand, we say that there are cases in which the optimizer is when S is less than 1/2. This, for what I've seen, happens a lot for human displacements. But this, I would say, will need another type of model, because for humans, once you move, that you move more or you move less is somehow less decisive. Okay, so here for human movements, it may be worth to allow very, very long jumps just because you don't pay the length that you travel after. I mean, travel to Australia or travel to New Zealand sounds more or less the same for a human, but not for a bird necessarily, right?
Yeah, so in any case, you yourself, you are in the levy regime, right? Jumping from Italy to Australia, right?
Yes, yes.
Yeah, that's not Brownian. Okay, thank you, Enrico. It was a very inspiring talk. I'm sure there will be further discussion. So we have to move on now. Thank you again. See you later. We have to move on now to keep track of the program. The next speaker this morning is Christoph. I think he's there. Oh, by the way, someone asked me, Emmanuel asked me, where is this pie picture taken? And I should say that it was taken in the port of Syracuse with my friend Giuseppe Floridia, that took me to a trip in Napoli and then to Sicily. And then in the port of Syracuse, I mean, in honor of Archimedes, in the ground, there is a small square where all these, mathematical symbols are graved. And this is indeed a beautiful place, right? So the only risk when you go there is that every day you gain 1 kilo because of the quality of the food. Other than that, it's a perfect trip. Okay, so I don't see Christoph, but I think he's there.
I'm here.
Okay, hello. Salut,
yeah.
Christoph. Salut,
Hi.
bonjour.
Salut. Yeah, okay.
So, yeah, thank you. You are in. So can you share your slides? Let's see if it works.
Yes, let's see. It should work. And
Very
it should
good.
be in full screen right now.
Yeah. So Christoph is he was with us for this academic year, formerly PhD student in Paris 6, next year in INRIA Nancy, I think, and now in transition somewhere in France, probably, right, Christoph?
Yes.
And
exactly
yeah, so today he's lecturing on the control of heat equations with shapes.
Yes, thanks for the introduction, Enrique. I have to confess, I thought the pie picture was from Erlangen, and I was kind of, I was afraid I'd missed something in Erlangen and that I would have to come back. So, okay, but Syracuse it is. Right, so as Enrique said, I'm going to be presenting our recent results that we have obtained on the control of heat equation with shapes. The more general question here that we're asking is, we're taking a very simple heat equation, a linear one with directly boundary conditions here, for example, and with an internal control. And then what we're asking is that this internal control should satisfy a set of constraints, right? Typically positivity constraints or pointwise constraints, upper and lower, or mass constraints. And then the question is, depending on the set of constraints that you choose, how do the controllability properties of the system change? And for example, one typical question would be, when does a phenomenon such as minimal time appear? Now, for the results I'm going to present today, we've focused on a specific type of constraints that we have called shapes. So as you can see here, we're interested in L2 controls. There is a size constraint on the supports, and the control can take only the values 0 or m, where m is a positive real number. So it's scalar multiples of characteristic functions, and the support cannot be greater than a certain value. Right? So here it's not really shapes, it's a relaxed shape control. And if m is equal to 1, then we have the real shapes. Now the result that we have is for the set of relaxed shapes, it's a result of approximate controllability. So given a parameter mu for the size constraints, given a final time t and a precision epsilon, any non-negative state in L2 is approximately reachable with precision epsilon, starting from 0 in time t with a control that is going to be a shape for almost every time. Right. And one important feature of this result is that the amplitude of the shape depends on the final time, on the parameter mu, on the target, and on the precision epsilon. Now, there's some simple things that we can say about this amplitude. For example, if mu, y1, and epsilon are fixed, it's decreasing with the final time t. This is quite intuitive, right? If you are giving yourself more time to reach the same targets, it will require less intensive work, and so the amplitude should be smaller. Another simple thing that one can say is that if you have two targets and one is consistently smaller than the other, so here y1 is smaller than y2, then the amplitude to reach y1 is going to be smaller than the amplitude to reach y2 for the same reasons. And then we could also try to look at how it behaves with respect to mu and epsilon, but it's not quite as intuitive. One might imagine that it's increasing with mu, that it's decreasing with mu, and that it's also and that it's increasing with epsilon. Right. Now, as I've said, we're dealing with a simple linear equation, right, with an internal control. But the thing is, because we're putting constraints on the control, it's not a standard linear controllability problem. Now, there are different ways one could imagine dealing with this. For example, there have been papers in the 90s by Hapalov that deal with moving control problems. And so one could imagine here that to model the movement of the shape of the control, one could use a transport equation, thus bringing back the problem into the realm of linear control theory. But what we've done instead is lean into the nonlinearity of the problem and try to look at it from an optimal controllability point of view. But the thing is, for an optimal control approach, it would be better to have a convex set of constraints, which is not quite the case yet. So what we've done is relax the constraints. That is, look at a larger set of constraints, right, that it contains the original set of constraints and should be convex, right? So some of the constraints are going to be preserved, and some are going to have to be dropped. And now in this new convex constraint set, then one can look for a cost such that the solutions to the optimal control problem would be controls that are actually in the original set of constraints. So this is very close to bang-bang controls where optimal controls are actually extremal. So this is kind of what we're looking for here. And so we have 2 degrees of freedom in this approach. The first one is, well, which constraints do we drop? Which constraints do we preserve? So how do we relax the constraints? And then once we've done that, what cost do we choose? And the idea is that choosing the cost should compensate for the constraints that you've dropped. And actually, it's a bit more complicated than that. It so happens that what we found to work is to take a very relaxed constraint set. We've dropped almost everything, and the only thing we kept is positivity. So we dropped the upper bound and we dropped the size constraints on the shapes. And now we're only looking at positive controls. So it's a very loose convexification, but the thing is, it's loose, so it gives us more space and more possibilities to look for the appropriate cost that is going to give us our shape controls. Now, before we start looking for the cost, so let's just settle once and for all the type of optimal control problem we're looking at. We have a fixed final time, we have positivity constraints on the control, we have a fixed precision epsilon for the approximate controllability, and we're going to be starting from the initial state 0. So that means one important operator is going to be the input-output operator, so it's LT here. So it maps a control U to the final state Y of t when you start from the initial state 0 and you take the control U. And now we're looking at this optimal control problem. Right? We're looking for admissible controls that minimize a given cost, and we're going to be trying to define this cost. So the first thing that we do is that we rewrite this optimal control problem to remove all the constraints from the subscripts of the infimum. So that means we're writing everything in terms of functions. So we're encoding the positivity constraint with that rho plus function. And notice here that it's a very strong penalization. So we're allowing for functions that take the value plus infinity here. And then we use the function g here to encode approximate controllability in the same way. So now everything is written in terms of functions, and we don't have any more constraints in the infinite. So this is the type of convex optimization problem that we're going to be looking at. So now, let's make a short intermission and introduce some important notions of convex analysis we'll be using in this relaxation approach. So as I've said, we're looking at convex functions on Hilbert spaces, and we should keep in mind that they can take the value plus infinity on a subdomain or on a subspace of the Hilbert space. The first important notion that we're going to be using in convex analysis is that of convex conjugate. So the definition is given here. So in a way, it's the solution. It's the value of this constrained maximization problem on the scalar product. Right, so this is a very classical notion. It's widely used in convex optimization, and it's also closely linked to the second notion, which is the subdifferential. So the subdifferential is a convex generalization of the gradient. Right, the gradient is one linear form, and the subdifferential is a collection of linear forms. Right, the most intuitive way to look at it is to take a 1D function of one variable, and as you can see here, we're looking at that point, that singularity here, and it has a left derivative and a right derivative. And the subdifferential is the collection of the slopes of all the lines that you can put under that graph and that pass through that point. So here, for example, you've got the left derivative and the right derivative, and the subdifferential is just the interval from A to B. And so it's really just convex generalization of the gradients. Now that we have these two notions, we can talk about the most important notion of convex optimization that we've been using, which is Fenchel-Rockefeller duality. So now we're working with two Hilbert spaces, two convex functions on these spaces, and the linear operator between the two, and we're looking at this optimization problem, which we call the primal problem. Now this is really the abstract form of the optimal control problem that I've presented a few slides before. The F part here encodes the cost and the constraints on the control, and the G part here encodes really approximate controllability. But really here now we're looking just at an abstract convex optimization problem. And for this optimization problem, we can define something that is called the dual problem using convex conjugates, so F star and G star here, right? And this is a new optimization problem, and it's closely linked to the first. The first easy link, let's say, using just the definition of the convex conjugates, is that the value of the first optimization problem is always greater than the value of the second optimization problem. Right, so this second problem is sort of a reflection of the first optimization problem, and the reflection is always under. And now what's remarkable is that under certain assumptions on the functions f and g, so in a way f and g have to be not too separated from each other, then you have something better. You have strong duality, which means that the values of the problems are actually equal. And even more interesting, the minimum of the dual problem is attained. So this is interesting because in applications, the dual problem, so the reflection of the first problem, of the original optimization problem, has often a nicer form, right? Remember that here, the primal problem, my primal problem, is this optimal control problem, and it's got constraints, which is not very nice. But when you take the dual problem, usually these constraints are incorporated, and the new optimization problem has a nicer form. And what's more, you have the additional information that the minimum is going to be attained. So all of this is useful to find the value of the optimization problem. But what we're more interested in is to find the optimizers, right? Because the optimizers of the primal problem are going to be the optimal controls. And these are what we want to be shapes. So how do we find optimizers? Well, in the case of strong duality, we know that minimizers for the dual problem exist. So we're going to try and see how we can use the minimizers of the dual problem to find minimizers for the primal problem. Now, suppose that we're given a minimizer for the dual problem. Using a property of the subdifferential, which is just the generalization of the fact that the differential at an optimum point is 0, we get that 0 is in this sum of subdifferentials. This can be interpreted as there is something in the intersection of two sets, right? So there exists an X star that satisfies these two conditions. So X star is in this subdifferential and AX star is in this subdifferential. And now, and this is another classical property, which is due to the link between convex conjugates and subdifferential. You can sort of flip the subdifferentials, and you get these conditions on Y star. And now these two conditions on Y star, you can rewrite them as a sum of subdifferentials, and you find that 0 is in this subdifferential. So this is, again, the property of subdifferentials in relation to minimization or maximization. And this tells us that X star here is a minimizer for the primal problem. So from Y star, we've been able to find a minimizer for the primal problem. So the dual, a dual minimizer gives us a primal minimizer. And we've been able to give some characterization of it, right, with two conditions in terms of subdifferentials. Now, coming back to our controllability problem, what's going to be interesting is mainly the first, which characterizes the control, right? Because the second is mainly telling us, okay, so the control is admissible. It actually achieves approximate controllability, right? So all of this is a bit abstract, and it's really convex analysis. And we've got okay, these abstract notations with subdifferentials. But what we're doing really is a convex generalization of HUM. Right? There's a way to interpret HUM for linear systems, right? When you're trying to minimize the L2 norm of the control, there's a way to interpret it where you're trying to minimize this functional, right? But this functional is precisely the dual optimization problem that I've been talking about in the previous slides. Now, if you find a minimizer for that functional, then you get an expression for the optimal control directly, right? The famous HUM control. I'm just gonna close my window, sorry. So you get an expression for the optimal control from the dual optimizer, but it's quite straightforward here because everything is differentiable, right? It's not so nice in the general convex case, but we still have the same kind of path, right? The minimizer of the dual problem gives us a minimizer for the primal problem. So now let's see how all of this translates in the case of the heat equation and how all of this can help us find an appropriate cost for our shape control problem. Now, so we're working now with L2 spaces, right? And as I've said, the F part is mainly the cost and the constraints on the control. The linear operator is here the input-output operator, LT, and the G part is the one that encodes approximate controllability. Now, let's suppose that we're given a dual optimizer. We still don't know what the dual problem is. We don't know what the primal problem is because we haven't defined a cost yet. But let's just suppose for a moment that we have an optimizer for the dual problem. And let's see how this can give us indications as to what cost we should take to find shape controls. Now, as we've seen, there's a way to characterize the optimal control using the dual optimizer and using subdifferentials, right? And this is just the definition of the subdifferential, right? But now we can tinker with this argmax expression, and we can see after some tinkering that this optimal control U star should be a constrained maximizer of this scalar product. And now this is interesting because in the context of optimization, there's a result called the bathtub principle, which is precisely about constrained maximization of scalar products. All right, so we're given a measurable function. We're trying to really maximize the scalar product with that measurable function under point-wise constraints and mass constraints, which is almost exactly what we have for shape controls. Right. And what this result tells us is that the maximizers are given by this following expression. So you have a shape component, the green one, the one we like, and then you have this degree of freedom, the red one, this where you have a lot of liberty, and which is due to the existence of level sets in the measurable function V, right? So this is nice, right? It's pretty intuitive, actually, when you're trying to capture a maximum of mass for a measurable function with a limited budget. What you're going to try to do is go around the peaks of the function, right? And then go down around the peaks. So for example, if you have a limited budget in red, you're only going to be around one peak. But if you have a bit more budget, like in yellow, then you're going to be working on two peaks. And this is called the bathtub principle, because now if you invert everything, this is what happens when you're filling a weird shaped bathtub with water, right? The water is going to go in the deepest parts first. Then if you've got more water, then you're going to put some of it in more shallow parts. Anyway, so this is the bathtub principle. But now let's get back to the heat equation again. How do we get into the bathtub with our heat equation? So as I've said, the optimal control linked with this dual optimizer should be given by the constraints maximization of a scalar product, right? And what can we act on to put ourselves in the bathtub? Well, we can choose the cost, right? And well, the bathtub principle is constraint optimization with a pointwise constraint and a mass constraint. So let's do just that. Let's put both in the cost, pointwise constraint here, a mass constraint here. And if we do this, it so happens that we are almost exactly in the context of the bathtub principle. And what is happening to define this optimal control is that at every time we're trying to fill a bathtub. But every time a renormalized optimal control here should be in this family. So there's the shape component that we like, and then there's this non-shape component that we don't like. And now the thing is, this red part, as I've said, it's due to the existence of level sets for that function that is in the scalar product here. But now, what's nice is that this P star here, it's the solution of a heat equation. So it's the solution of the adjoint heat equation, right? So it has a smoothing property. And in particular, what this implies is that the level sets are of zero measure. So actually what we have obtained is that this optimal control that is characterized using the dual optimizer is actually just a shape control, and it's even uniquely defined. So to sum up, given that cost, so with a pointwise component and a mass component, right? If with that cost, we can find a dual optimizer, minimizer for the dual optimization problem, then the optimal control is uniquely defined. It's defined by this subdifferential set here, because this subdifferential set is just a singleton, right? And so it's the only one it's the only possibility for the optimal control. So it's also going to satisfy this and be admissible, right? And we can give the expression of this unique optimal control as follows. Now there remains some questions. Does the dual optimizer exist? Does PT star exist? And then also, well, we have a shape here, and then we have the amplitude of the shape, and we like to know a bit more about the amplitude of the shape to get a better picture of the controllability results. Let's do just that. Let's first look for a PT star. So remember that we are working with a target Y1 and that we want to reach with epsilon precision, right? And this now allows us to define the dual problem, right? So this is the abstract notation of the dual problem, and the notation in our heat equation context is dysfunctional. So notice that it's quite similar to the kind of functionals we have in the Hilbert uniqueness methods, right? There's this part here because we have approximate controllability, so there's an additional penalization, and well, as you can see here, in HUM, we'd be capturing the whole L2 norm of the adjoint states. And here, because we have more constraints, we have a limited budget. We're not capturing all the information of the adjoint state. We're only capturing as much information as we can with our budget, right? So we're only capturing some of the positive mass of the adjoint vector, right? Now with this functional, even though it's a bit different from HUM, we can still prove that it's lower semi-continuous, it's convex, it's proper, it's coercive, and thus it reaches its minimum. So this guarantees the existence of a dual minimizer PT star. We don't really know what it looks like, but we know that it exists. So all that we've said before about defining the optimal control from a given dual minimizer, all of this holds. And so the optimal control exists. Now all that remains is to try and have an idea of what this sigma star, what this amplitude is. And to do this, we use one last time the relationship between subdifferential and convex conjugates, which is here, right? And we just replace, right, U star by its expression, F star by its expression, C by its expression. We know that C of U star is going to just be sigma star, and we have this equation in sigma star. And so we solve it, and it turns out that sigma star is just this simple expression. So that means that the final optimal control, the final expression, is here. So you can see that the amplitude is the total mass, the total information that we've been able to capture on the adjoint vector, right? So now we have a more complete picture of what this optimal control is. So to sum up what we've done, so we've tinkered a bit, we've remembered that we have a bathtub principle, and this has allowed us to propose a cost C. And then using convex conjugation, this allows us to define the dual problem, and then we can solve the dual problem with basic convex optimization. We find a minimizer for the dual problem, which is PT star, and then using subdifferentials and abstract considerations in convex analysis, and then some smoothing properties of the heat equation, we can characterize uniquely the optimal control U star. And we can give its amplitude, and we can give a quite complete expression of that control using PT star and the associated solution to the dual, well, to the adjoint of the heat equation. Right. So to sum up, we have obtained approximate controllability of the heat equation from 0 to non-negative states using shape controls. In particular, what this implies is that any non-negative state can be reached from 0 using non-negative controls, right? Because we've done it with additional constraints, but in particular, we've obtained the results with only positive constraints. As I've said before, so the amplitude of there is an amplitude in front of the shape, right? Our optimal controls are not exactly shapes, they're multiples of shapes. And we've given the expression of the amplitude here. It all hinges on that P star, which is linked to the minimizer of the dual functional. We've already said that it's decreasing in T. So this implies in particular that for T large enough, well, you can find a T such that M of T mu y1 epsilon is 1. And then you would have a real shape. So the question is that, does this mean that for real shape control, there's minimal time, or is it just that taking this approach makes a minimal time appear? But it could well be that, for example, there's no minimal time if you're trying to control with real shapes with amplitude 1. But what would happen is that if you only give a very small time, then the shape of the control is going to be increasingly complex, right? It might be that there's no minimal time, but there's a minimal complexity of the control. So this is still an open question, which I find really interesting. So we've obtained these results using a relaxation approach. We've relaxed the constraints. And then on this relaxed constraint set, we've used general convex analysis tool. So mainly subdifferentials, convex conjugates, and Fenchel-Rockefeller duality. Now, because we've been using quite general convex analysis tools, this leads to two questions. Can this approach be adapted to other equation with the same type of shape constraints? And then the other question, keeping, for example, the heat equation, could this be extended to other constraints? And what would the controls look like in that case? And what would the cost be in that case? And on these two questions, I will end here, and I thank you for your attention.
Thank you, Christophe. Thank you for the interesting talk. Are there questions or comments? Okay, if not, since we are a little bit late, then we go to the next, and there will be time in the coffee break to continue the discussion. So let's move on. The next speaker this morning is Marius Tuxnack. So is Marius there? Mario?
Yes, I'm here. Do you hear me?
Yeah, we hear you and we see you. Yeah. Okay. Yeah. So do you have some slides to share?
I will try to do that.
Oh, fine. So thank you, Marius. Yeah, okay. So it's for me a great pleasure to introduce Marius Tuxnack. You know him, most of you. Marius is a chair professor at the Université de Bordeaux. Before that, he was a professor in Nancy, also the founder of a new INRIA team in Nancy, where we had also many colleagues like Takeo Takahashi and Ludovic Gagnon and several others. And well, Marius has a very broad spectrum of interest. So fluid structure interaction. He has also this beautiful book with George Weiss, more abstract control theory. But today he's talking about something else. He's talking about the control of infinite dimensional systems with H structure. So, well, I don't see the interest of analyzing age, but still, I mean, Marius is free to, yeah, he was free to choose the topic, and this is what he decided to lecture on. Thank you, Marius.
Thank you very much, Enrique, for the introduction. Thank you, Giuseppe, for all your efforts to organize this successful meeting. So what I will discuss is essentially how to graft an age structure on a given infinite-dimensional linear system while keeping most of its nice properties. So, to be more precise, many systems coming from physics, biology, or other fields are, let's say, it is possible to linearize them and then to get an equation, quite abstract, a quite general form, which writes P dot is equal to AP plus BU, where A will be a generator of semigroup in some state space, which will be denoted by capital X, and B, so the red term, BU, it's a control term. It shows the way in which we can influence the system. Of course, this is very abstract. Is not abstract at all if A and B and are matrices, and which is the initial, let's say, framework where controllability and observability theory has been developed since Kalman. But it becomes a bit more abstract when we deal with PDEs, namely with boundary control. So if we deal with boundary control PDEs, this operator B will be something called the unbounded control operator. This is translated mathematically by the fact that B maps the control space, which is denoted by capital U, to a space X denoted by X minus 1, which is larger than the state space X. So this is a very general fact, and many equations which we with partial differential equations, which we have seen, can be written in this manner when they are controlled from the interior or from the boundary, like heat, wave, or Schrödinger type equations. In the case of these PDEs, the state P of T lies in an infinite dimensional Hilbert space at each instant T. More specifically, P depends not only on time, but also on X, a space variable, in the case in which we have a PDE system. It turns out that in many cases, namely for a biological system, there is another dependence which plays an important role. It's the dependence with respect to the age, namely of individuals. So in population dynamic, for instance, of course, age plays a central role. More recently, we have seen a lot of epidemiological models, which have been a lot studied with the COVID outbreak. Most of them don't have the age inside, but many of them have, and the age appears in two ways in this epidemiological model. One way is, of course, the biological age of individuals, and another way is the age of infection. So at the beginning of the outbreak, you remember, it was said that it was explained, it is still true, but maybe it's evolving. It was said that let's say the gravity of the disease is maximal 8 years after. So this 8 days after being contaminated, this was an age of infection. Nevertheless, it was also said that older people are more likely to get serious forms. Here, the age appearing in the model is a different one. In some modelings of this problem, people even worked with both ages simultaneously. So P was depending not on X, very few, let's say, studies have been done with P depending on X, but P was depending on time, on the age, biological age, and on the age of infection. But I will not discuss these models in this framework. So the most simple way to let's say, to take in consideration the influence of age on the evolution of a population P, this is why I denote the state of the system with P, is, of course, to say that P depends not only on T and possibly on a space variable, but also on the age. And then to the original equation, the first thing is to add the term dP over dA, since with the exception of Enrique, everybody gets older nowadays. So this is the aging term. Then there is also a mortality term, which depends on the age, mortality coefficient mu, which will be positive. I will say something more immediately on possibilities for on assumptions on this coefficient. And then we can add some control. The control was already there. If you remember, I had already a B, but the control can depend on age, and also the control operator can depend on age. This is why I multiplied the original B operator by a function key depending on age. What's also important is that in age-structured models, you have births in general, so we have what's called the renewal equation. The population at instant of age 0, so the newborns at instant t, the total number of newborns at instant t is given by the integral from 0 to a maximal age, which is denoted with a plus. So we suppose that there is a maximal age here, finite, of some beta of a, which is the birth rate, times the total population. The main questions which I will address mathematically in this talk are concern the well-posedness and the controllability in an appropriate sense of this new system by assuming that these properties hold for the original one. So methodologically speaking, the main novelty which we bring here is that we don't care about the way in which, for instance, controllability has been obtained for the original system. It means the one without age. And we just prove that under appropriate assumption, these properties can be translated for the age structured systems. There are also novelties at the level of the results. So doing like this allows improving even some existing results on specific examples. What about mortality and for fertility? So a typical fertility rate is the red curve. So you have age in the abscissa, and on the other axis you have for the red curve you have beta of a. So it is reasonable, but not always let's say pertinent to say that the birth rate is a compactly supported function. So population at very early stages or at very late stages cannot reproduce. So this is, of course, something which looks natural for population dynamics, but in epidemiology it is not at all the case. So one can be contagious from the beginning of the infection. So this curve is typical for many applications. So we will make this assumption, but it's not, let's say, very typical for epidemiological ones. Concerning the mortality rate, this is, let's say, quite general. It's a blue curve. It is assumed that it has an asymptote when at the maximal age, a is equal to a plus here. But of course, it is also supposed that it is an L1 function. So these are typical, and these will be more or less the assumptions, the type of assumptions which will be done throughout this work. The first example is, of course, to take the original system, just a linear ODE system. So I choose the state space X is equal to Rn. U will be Rm, so it's a control space. And then I assume that the matrices A and B satisfy the classical Kalman rank condition, which is written here. The rank of this Kalman matrix is maximal 1. And then it is known that the original ODE system, Z dot is equal to AZ plus BU, is controllable. There is only one notion of controllability for finite dimensional linear systems. Then we can, of course, do what I said previously, add an H structure. Let us take it in the very simplest case where the input space X and the control space U are just the C or R, as you prefer. A is just the zero matrix and B is equal to 1. The system is extremely controllable. This matrix, the system AB is clearly controllable. And doing this and adding the H structure, we obtain the classical Lotka-McKendrick system with the H structures. So what is P of T and A? P of T and A is the distribution density of the population of HA at time T. A star is the maximal life expectancy. And mu and beta, as already mentioned, are the mortality and fertility rates. So if I had a result allowing me to transpose controllability from the original AB system to the system enriched with the H structure, then the null controllability, for instance, of the system would be an extremely simple result. It turns out that this system has been studied by direct methods long time ago by Barbu, Ianelli, and Marcheva, which have shown, and it is not easy, in fact, if you take a lead directly, which has shown directly some null controllability results. I will maybe mention again this example because it's probably the most simple and the most relevant one. Second example, so here we can assume that, so it's just a way, in a certain sense to complicate a bit this Lotka-McKendrick type model. We add a variable, which is a space variable x. So P depends on time, age, and on the space variable x. And there is some transport at constant velocity. So you can think of particles which are transported by a river, which flows at a given velocity, small v. Then there is the partial differential equation is dp over dt plus dp over di. I remind this is the aging term, plus v dp over dx, and then the other terms are more or less the same. And also here, our control can act from the boundary. That's also nice, since we add the space variable. So we can add a control at the left, a control of birth, not of birth, sorry, at the left end of the space interval we are considering. And this control can be active for a certain age range and depend itself on age. And then there is the usual renewal equation, which here in which X, the space position, is just like a parameter. Again, this fits into our framework for the original system. So without H, X is L2 of the interval 0L. U is the real numbers, a set of real numbers. And the original operator A is just the transport operator defined here on H1 with domain formed of those H1 functions which vanish at the left end. Whereas the control operator B is just the Dirac mass concentrated at X equal to 0. So as far as I know, very few things have been studied for this transport coupled with H structure. Our results, which will be precisely stated immediately, give quite sharp controllability results for this system also. A system which has been studied much more and which motivated, in fact, our abstract approach is diffusion coupled with H structure. So here I have still the space variable X, but my PD with respect to the space variable is essentially the heat equation. And I add a control inside the domain. This control is active only in a certain age range and for a certain spatial domain. And again, all the rest is the same. To make things precise, what is P here is the distribution density of the population of H at spatial position X and the time T. Again, I have a maximal life expectancy and the diffusion coefficient K, which I take here constant. In fact, is not an essential thing for getting nice results. So on this model, we first did a paper with Enrique Zuazua at the MIT, where we improved a lot of the existing estimates, controllability estimates, and then we realized that a big part of what we are doing could be better described and even better understood once we go to an abstract level. So these examples, I try to give examples which make some biological sense. Of course, nothing forbids to give examples which, to my knowledge, have no biological sense. So I can take a Schrödinger equation with H structure. Again, all our philosophy would work. But of course, so this in this case, the operator A would be chosen minus I times Laplacian, and B would be a distributed control operator. To my knowledge, there is no real application of this kind of model, but mathematically it makes sense. So to say something about previous work on this field, everything was focused on specific models, and essentially either on the initial Lotka-McKendrick model, so where P depends only on time and on H, or on the model with H dependence, H structure, and space dependence, and more precisely on the model with diffusion. So diffusion coupled to H structure. So the parabolic, some people call this ultra parabolic problems. So to my knowledge, the first semi-group approach for the diffusion H structure problem is due to Chan and Guo. Then there are people which have been working on optimal control, on controllability, often with using, for instance, in the parabolic case, the Kahneman inequalities. Also, some works concerning inverse problem, and also numerical methods have been developed which require a lot of attention in these H-structured problems. So the remaining part of the talk has this outline. I will say 2 words about semi-group formulation, then about L2 null controllability, controllability with positivity constraints, and I will try then to conclude. So the semigroup formulation, I'll try to go very quickly on that. So I remind that I already had a semigroup formulation on the original problem. The state space was capital X here, and the control space was U. So now what I do is just let's say augment them to curly X for the state space, which is L2 of functions L2 with respect to H with values in X. So the dependence of H, we embed it in the state space and also in the control space U. And then so this operator A, straight A, had already a domain. And then we can define a new domain for the operator curly A. And with the right assumptions on A and on B, we can show, and this is our theorem from with Deban Maiti and Enrique Zuazua from 2019, that if the original operator A was generating a semigroup, not other assumption, it's just C0 semigroup, then curly A will also be a semigroup generator on the space curly X. And if B is admissible, I don't enter into the detail of admissibility. But so in other words, if our initial problem with control was well posed, then the same holds for the problem where I have added the H structure. So I will try to skip this this part. So what is important, and to my knowledge, is not a lot done. At least not very explicit in the literature, is to look to the adjoint of this operator A star. If you look to the literature, there is only in general one line. Take the adjoint problem. But in fact, if you want to be extremely rigorous, which I try to be, you need to compute formally the adjoint of this operator A star, and there is some work which I just mentioned that is important to do it, but I will not detail here. And now, in general, indeed, we take controls which are L2 with respect to time and L2 with respect to the space variable in a PDE control. And indeed, we have here this theorem, which says that assuming that the very young population is not fertile, so the fertility rate is 0 at very low ages, then we have an observability inequality for the adjoint problem. Thus, let us look only to the corollary. I have exact a null controllability. That's very essential. The type of controllability I can hope is only null controllability. Impossible to have exact controllability in a time which depends on the maximal age, on the minimal controllability time of the initial problem without age, and on the support of the control. So my control is supported between A1 and A2, if I remember correctly. So, and this is the proof, which I will not detail, which is, in fact, just using the information we had on the problem without age. The way it uses it, it's pretty classical. It uses it going on characteristic and propagating the information which we have for the problem without age. So working with this characteristic is quite typical in population dynamic problems. So I'll try to not to abuse of your time. So we have several types of controllabilities. We can have controllability from the boundary. This is new.
There are 11, 12 minutes.
How many?
11, 12 minutes.
I still have this. Okay, thanks a lot, because I was a bit maybe going too quickly. This is the way we do that. So controllability, what is important is to have a beginning of an age from which we control the beginning of the interval before the minimal birth rate, which is means somehow that we are controlling also births, which maybe doesn't look realistic. Of course, for instance, in epidemiology, this is impossible to do. But this is why we obtain a result which is also extremely strong, which is we have null controllability, or since the problem is linear, we have exact controllability to trajectories. Nevertheless, I will try to skip these technical parts where, in fact, what we use is duality. We use the duality between null controllability and the final state observability. And in fact, what we prove is the final state observability inequality. And the way we prove it is just by propagating, of course, final state observability for the adjoint problem. And we propagate the information we have for the problem without age. So I will try to say 2 words about controllability with positivity constraints. So what we discussed till here is very much inspired by the usual approach in infinite dimensional system theory, which is to work with Hilbert spaces and with controls which are L2 with respect to time. This is not so relevant in population dynamics, for instance. The relevant space is L1. So because when you want to look to the total population, you just integrate. And also there is something which is, it can also be eventually L infinity. And if you are on a bounded time interval, I mean with respect to age, then of course L infinity is even better for the population, which, as you know very well, are not Hilbert spaces, L1 or L infinity. And also there is something else which is important. Population needs to be positive at every time. This is something completely ignored, but what we discussed till now. So how can we handle these constraints? So to do this, we may need to be more specific. We need first to say that what we want is not to control to 0. In general, we don't want to control a population to 0. We want to control it to a steady state of the system. So I introduced the notion of steady state of my previous abstract system. And here L is the operator, which is in general a kind of elliptic operator in PD type models. And so here I don't have longer the time, and I introduce a steady state in the presence of a steady input, which is Vs. So this is the approach which appears, for instance, in the paper of Barbu, Yaneri, and Marcheva. And of course, everything else is preserved. There are still births, but let us say we want the population at point X to be independent of time. And we assume that this steady state, if it exists, is strictly positive for some age interval which goes to 0, from 0 to A star. So A star is not the maximal age. So I don't assume that you have strictly positive population at every age. The first question is, does this type of states exist? So it's not such a clear problem for precise models. It is true if the basic reproduction number is 1, then there is an infinity of them. But otherwise, if it's smaller than 1, there is not such a state, because the population is not unstable. It will go to 0 if R is smaller than 1. What does our main result say? Say that if I have such a state, so there are conditions in which such a state exists, steady state, then there exists a control time, and the control which is just L infinity with respect to time and to age and even to the space variable, such that the solution of time tau is exactly the steady state solution, and the population is positive all the time. All the time, and here it should be a t, not a tau. Sorry for that. So it's positive at every time, at every age, and at every space variable. So what happens here is when I say there exists a time, this time will depend on the distance between the initial state of the system and the final steady state. So this is not, but in fact, you know this already from the heat equation, from the works of Emmanuel and Enrique and Jérôme Louverc, where you know that for a heat equation, the simplest one, linear, if you want to control while preserving positivity, you need a minimal time. So in this problem, we already needed a minimal time because of the age structure, which gives some hyperbolic character to our problem. But it was uniform till now with respect to the initial state. Now it depends on the initial state, which is also very coherent with what we know for instance, the heat equation. So to do this, in fact, what we need are L-infinity estimates, first for the direct problem. So this is what is in the proposition up. So L-infinity estimates for the direct equation, for the state equation, without control. So no, even with control, which is distributed, which was not existing in the literature, but which was known, for instance, for the heat equation. So all this part, let me say, is for the case of diffusion. So the operator L is an elliptic operator. The operator L, which appeared here, it's a second order elliptic operator with smooth coefficients. So you can take it the Laplacian minus Laplacian if you prefer. So first get L-infinity estimate, in fact, again characteristics and reducing the problem to the similar estimates for the heat equation. What is interesting is the observability inequality we need here. What we need here for the adjoint state Q is this observability inequality, which if we look carefully, the observation, the problem is that the observation Q of TAX is at L1. We need here, when we go to the duality process, to measure the L1 norm of the observation. Small omega is the control domain. And here at the left, I have the L2 norm of the final state. So for the moment, I keep the L2 norm of the final state. But what I'm doing here is that I observe only the L1 norm, which a priori is smaller than the L2 one. And so with this, we get by duality a control which is L-infinity and a state which is L-infinity. And this is extremely nice, because this is why I can try to control the sign of P. And to control the sign of T, we are proceeding by an iterative process. We go by small steps. This is what my colleagues already mentioned have been doing for the heat equation. Essentially, it's the same thing with an extra difficulty, which we need to take tackle very careful, which is that my equilibrium state is not strictly positive everywhere. It's strictly positive only up to a certain A star. So we have to distinguish between two age intervals and do this very carefully. Nevertheless, by going very slowly, we are able to steer the initial state supposed positive to the final steady state positive and strictly positive on a subinterval. So I will go now to some conclusions, which maybe I will enrich with some comments. So we have obtained the controllability results for Lotka-McKendrick with an age structure in a sharp time, and what's interesting, without excluding low ages. All the results which have been seen in the literature were controlling all the populations, but not a small interval beginning with 0. And then, of course, not only for Lotka-McKendrick with diffusion, but also with, I would say, Lotka-McKendrick with transport and many other examples which can be in a certain manner, let's say, imagined. Last, also quite importantly, we have obtained controllability with positivity constraints in a time large enough. This is clearly important for the real applications we have in mind. Questions to be tackled, which are quite natural, and the first one would be, what about nonlinear models? How can we get a, let's say, nonlinear model making sense is to assume that mortality and or fertility depends on the total population, for instance. This is something typically done in population dynamic. What about competing populations, so prey-predator models? And then an interesting question is, I don't know if it really makes sense in population dynamics or in epidemiology, is feedback control. Up to now, we had open loop control. So I personally think that feedback control in the traditional sense would not make sense, because it means that you have data and you react instantaneously, but which makes sense and which has been implemented, for instance, by some very nice papers in, let's say, studying the COVID outbreak, was model predictive control. So put an input and at the same time using appropriate inputs to identify coefficients and then adapt your input to the new data. So model predictive control, which is a kind of feedback, but not in the traditional sense, seems a much more appropriate tool for this type of problems. So now I will think I will end my talk. Thanks for your attention, and I'm of course open to any questions or remarks.
Okay, thank you very much. Okay, there is the chairman. Okay.
Yeah. So yeah, thank you, Marius. Very interesting talk. Well, we have some time for questions and comments.
Ricky, I have a question.
Please, listen.
Thank you, Marius, for this very interesting talk. As you mentioned, in dynamic population equation, L1 is the appropriate space.
Yeah.
Because of the density of the population. But when for a real problem, mathematically, it's clear that you used L2 and it's a Hilbert space that it's make things easier. But when we show that the system is controllable for a dynamics, for a biologist, for example, where he will see that we used L2 or L1, I mean, at the end,
he will not see. So this is why for controllability, this is not, I think, has not an important effect on applications. But what has important effect, it's the positivity, and to be able even to speak about positivity, you need to control, in fact, not the L1, but the L infinity norm of the state. Mm-hmm. Because so what is important, in fact, it's more L infinity, which also makes sense. And even if you have controllability in L1, in L2, the controllability is proved in an L2 sense. But of course, if you take an initial state in L infinity, you can still control it to 0. And moreover, what we are proving is that you can control it to 0 while preserving positivity.
Yeah.
And if you don't do without L infinity, so the way we control it to 0, let me repeat, is that I know that I can go to a close state with a control which is small by perturbing not too much the solution. But to say that, I really need to measure the control cost, and then the control cost and the fact that the solution is still positive depends on the L infinity norm. So to be hoping to answer to your question, what is more important is L infinity for a biologist.
Okay, very good. Thank you very much.
So any further question or comment? Okay, so if not, we thank Marius and the speakers this morning again, or maybe there are other questions in the chat, let me see. No, thank you very much. Okay, so people are thanking for the talks. So as I said, we have now a short coffee break. Thank you all the speakers this morning. It was extremely interesting. And then we reconvene, Giuseppe, at what time?
11:20.
11:20. So we have 20 minutes break. Thank you all. See you later. Ciao.
Okay, next
Bye-bye, thanks.
Thank you. Next chairman will be Professor Masahiro Yamamoto. Next speaker, Martin Burger. Thank you. See you later after the coffee.
Already I'm here. See you.
See you.